Welcome, everybody. Thanks for attending again this series of seminars. We are back after this summer break. It's a pleasure to have you all here. And it's a pleasure also to thank Carlos Ramos Marimón, who is the speaker today. Carlos graduated by the University of Valencia, and then he went to Germany for his master's studies in Bonn and Köln. His master's thesis dealt with super-radiant transition in a Bose gas. Later, he went to Barcelona to do his doctorate, and he doctored actually last week, so he's a warm doctor. And his advisor was Luca Tagliacozzo, and therefore he's a specialist in tensor networks. Couldn't be otherwise. So his current interests are, however, manifold, quantum classical transition, thermalization, and the use of tensor networks. So since April this year, he works at Quobly as a research engineer, and today he will give us a seminar titled Off-Diagonal Pauli Weight Truncation and Equilibration Temperature Dependence for Stimulating Local Dynamics in Quantum Systems. Certainly a long and stimulating title for a seminar. So, Carlos, the floor is yours.
Thank you very much. So yeah, as Javier already said, this is content from my PhD. So it's something that we think it's quite nice because we got really nice results. And I wanted to mention, since despite Javier already mentioning that this work has been carried out at the Institute of Cosmological Sciences of the University of Barcelona and funded by La Caixa Foundation, which I also have to thank for supporting my research. And yeah, as I said, now I'm working at Quobly, which is specialized at producing hardware based on spin qubits for manufacturing quantum computers. And yeah, the topic today seems a bit, the title is a bit complex. So of course, let's try to uncover all the content of the title. And I propose for that the following index. First, I want to strongly set up which is the problem we want to tackle during this talk, which is that of quantum dynamics in quantum many-body systems, and in particular use the language of tensor networks to deal with it. And after formulating the problem, is going to be the main part because I want you to understand why this is important and why we want to do research on this direction. I will start commenting on one of the particular styles in which we can tackle this problem, which is Heisenberg picture evolution. And for Heisenberg picture, we introduce concepts like Pauli Weight, and we will review some of the proposals by other groups that worked on truncating Pauli weight. We will see what that does mean. And also we will propose our own method, which is a modification of other existing methods based on truncating Pauli weight. And of course, we will to characterize it and to test it and compare it with other methods that are also state of the art. And this will bring me to the conclusions. And also, if you're interested on these other methods that we're going to use as benchmarks, I also prepared some extra slides in case you want to take a look. Okay, so let's start with the block of quantum dynamics. And first of all, let's start from the very basics. The goal of my thesis and also the underlying goal of this particular topic that I want to talk about today is the numerical simulation of many-body quantum physics far from equilibrium. So let's unpack each one of these concepts step by step. First of all, quantum physics. It's the theory that we use to describe the microscopics. And of course, we have state vectors that live in a Hilbert space. This is the algebraic structure we are based on. And we elevate the observable quantities to observables. So matrices like the Hamiltonian that encodes the allowed energies of our systems. And each one of these energies can be labeled by quantum numbers once we are able to diagonalize the Hamiltonian. And already quite soon in the 1920s, 30s, simple problems that were single body problems were more or less well understood, like retrieving the Balmer spectral series from the hydrogen atom by solving the Schrödinger equation, or even quantizing the harmonic oscillator. But these are like the simplest problems. We want to tackle other kind of problems that actually were part of the trigger to develop quantum physics, and within this group of problems is understanding the properties of condensed matter systems. And with condensed matter, I mean here today solids. We can also consider quantum fluids, but these are out of the scope of my talk today. So we will consider organized structures or even amorphous, but fixed in time. And since we have many particles now, the Hilbert space required to describe this problem is the product, the outer product of the Hilbert spaces of each one of the local Hilbert spaces. And this brings computational growth that is exponential. Why? Just consider, for example, the case of spins, which is the subsystems that we're going to use as an example to illustrate our methods in this talk. We can have states for a single spin that are up or down, zeros or ones. And if we try to count all the available states, the combinations of up and down spins for a chain of n spins, then we have 10 to the power of n of dimensionality of the Hilbert space. And this is an exponential growth. The problem is going to become exponentially more difficult if we want to represent the information exactly. And just for illustration, imagine that we want to understand the physics of 4 spins in a grid, in a 2x2 grid. Then we just need 16 states, which is okay. But already for 16 spins, this is starting to get large. It's starting to get to the limits of memory if you want to fit the matrices involved in memory that your laptop can deal with. And if you want something like 128 spins on the side of the grid, then the amount of states it's not even imaginable for the human brain. So yeah, imagine that just a single piece of material that has like 10 to the power of 23 atoms. If we wanted to retrieve the properties of these realistic materials, then of course we are running out of resources, computationally speaking. So we need somehow to develop techniques to tackle this. And the problem underlying how to understand these condensed matter systems is connected to the interactions. I said that we elevate quantities like the energy to operators, and these operators can be interacting or non-interacting. If the operators are non-interacting, we can have analytical solutions, exact solutions. And for these exact solutions, then we can use as approximate correct eigenstates of the Hamiltonian product states, because we have low entanglement, low connection or interaction between the subparts of the system. And this was already quite good. For example, we can understand on a qualitative level band theory, the conduction of electrons, or whether a material is insulating, or even semiconductors, using a model that assumes that electrons are free particles. But of course, we cannot stay there. We wanted a bit more. We wanted to tackle interacting systems, and the first approaches were to try to eliminate interaction somehow, average them out, or even using perturbation theory. Perturbation theory is the easiest way, or the first thing that can come to our minds. We just expand in powers of a small coupling, and then we try to perform exact summations, but this is not amenable for all the systems. We get limited results that can be qualitatively nice, but usually not enough for complicated systems. And mean field consists on averaging over all the interactions on the environment. And for example, mean field was already quite successful at describing phases of matter. And with phases of matter, I mean states of many body systems with a well-defined extensive quantity, like a magnetization, which gives me an ordered parameter. And we can distinguish or explain transitions between paramagnetism and ferromagnetism, either in classical physics or in quantum physics. But not only magnetism, mean field was also able to explain explicitly quantum phases that only appear at extremely low temperatures, like superconductivity or Bose-Einstein condensation. And these two particular phases can help me to introduce the final problem, which is out of equilibrium physics. Why? Because when we have some system that is eminently strongly interacting, because conventional superconductors can be modeled with mean field, but high temperature superconductors cannot be modeled with mean field. The predictions of mean field break down quite soon. So we have a fully strongly interacting system from the beginning, a Fermi-Hubbard model. How do we solve it? We have questions even at equilibrium. We do not really understand the phase diagram and how do we transit from one phase to another. How does this picture change out of equilibrium? To understand it, we need to resort to other techniques like tensor networks. So numerical techniques like quantum Monte Carlo is also quite successful, but it's also based on perturbations. And exact summations are really limited. So we pick today tensor networks, which is one of the most competitive tools up to date. And to tackle out of equilibrium, we are interested in systems that are exposed to flows of energy, which are systems that by defect are much more complicated than equilibrium phases. And they give much more richer physics because we could stabilize phases like superconductivity at regimes of the phase diagram where we will not expect these phases, or even create new ones that were not existing, like super radiance. And just to put as an example some realistic works, we have this from the past 15 years. We had this publication on photoexcited superconductivity, where superconductivity was achieved in a regime where it was not existing at the beginning by putting some flow of energy, photoexcitation. But also understanding out of equilibrium physics can be really interesting also because some of the problems are intrinsically having transport of particles or of energy, and understanding or harnessing this physics can allow us to build new devices like those based on nano-optoelectronics or plasmonics. So this was mostly motivation. Now let's switch to how do we describe this apparently super complex problem with a language which is that of tensor networks. So we have to deal with the state vector, and whenever we want to represent a vector, what we have is we like to represent it as a shape with a single leg, and each one of the legs is going to label the entries of this array, this numerical entity. But of course, we could aim at a splitting of the indices in such a way that we can address each one of the local degrees of freedom. For the case of one-dimensional spin chains, we can imagine the whole array in a one-dimensional lattice, and we can separate the indices addressing each one of the spins. And this is just a numerical reshaping. We just have our array on memory, and we just give a reshape function, and we split the dimensions. But we want to go further. We would like to factorize this big tensor into smaller tensors that we can keep in memory. And the basic factorization we're going to use is called matrix product state, because in the process of factorizing, we're going to transform the coefficients of the superposition into traces over products of matrices. And the same can be conceived for density matrices, which is just an extension of the formulation in state vector form, but also allows us to deal with finite temperature systems or even with loss of information and dissipation. And also for observables, we can also represent them as tensor networks. And we are going to focus on those observables that are of interest for experiment, which are usually 1-point correlations or 2-point correlations. Today, we will focus on fully local ones. So we just have non-trivial action only on few sites or one site. And they also admit this matrix product form, but now it's a matrix product operator form. Okay, in the process of generating this splitting between the degrees of freedom, we have introduced new indices, and these new indices are those that are traced over in the rewriting of the coefficients of the superposition. Is this trace written in orange? And we call them virtual indices because they are dependent on which is the factorization that we picked. In principle, we could choose any internal structure. And the physical indices, here shaded in green, they are the ones that couple to observables. They are the one that we contract with the observable when we compute expectation values. And of course, each one of those have its own dimensionality. We call bond dimension chi for the dimension of the virtual indices, and physical dimension d, which in this case for spins is going to be equal to 2, to the dimension of the physical indices that couple to observables. And how do we couple these indices to observables? We perform the trace with a density matrix, and a trace in the language of tensor networks consists on connecting the legs. So depicting the following loop. But of course, painting loops every time can be a bit cumbersome for drawing complicated diagrams. So usually what we do is to fold the legs. And this means that we vectorize the arrays. So we flatten matrices. For example, if they were written in the basis of Pauli matrices, now we have a flattened basis of four vectors with 4 entries. And if we introduce also the dimension of space, then what we have is an overlap between matrix product states that originally was an overlap between matrix product operators, but in this flattened picture, we just have a 2D diagram, which is much easier to draw. And this diagram allows me to introduce another player, which is the reduced density matrix. Since I want to address local observables, we are usually going to trace over the rest of the system. If we trace over the rest of the system, actually, I just need the information on the few sites where my observables are going to act. And once I have the splitting between subsystem L and the rest of the system, I can name all these objects reduced density matrix. And the expectation value between this reduced density matrix and the operator is going to give me exactly the same results as for the global density matrix. Okay, so this was a setup about how to use the diagrams to describe the basic pieces of quantum many-body systems. Now, let's go to the problem of dynamics or out of equilibrium. In particular, we're going to describe the scenario of a quench. And to understand what a quench is, let's first introduce the 2 equations we would like to solve. For the case of the vector formulation, we have the Schrödinger equation, and for the density matrix, that allows us to solve other extended problems like thermal initial states, we can use von Neumann equation. The formal solution of these 2 problems corresponds to exponentiating these equations, and in the process we generate the exponential of the Hamiltonian with a complex unit. And the complex unit is going to transform this exponential of ht into a unitary operator which preserves energy. So this is the generic dynamics we want to solve. And now we have to plot it again by introducing the pieces, the Lego pieces, the tensor networks that we have introduced before. So for this formal solution, the network is going to look like this. I have my initial state here, and I want to compute the expectation value with some operator. So in between, I have my evolution, and since we are doing numerics, we want to address quantities at each step in time. This allows me to split the evolution operator into tiny pieces with size delta t, and this is nice because we cannot compute exactly the exponential of the Hamiltonian. If we could do it, then we will have solved all the problems of physics, most probably. But we cannot do it, so we go to this small delta t approximation, and this allows us to perform some decompositions like Trotter decomposition, or even we have also available MPO forms for the evolution for particular problems that I list here, or even W1 or W2 formulations. And this structure is amenable also for introducing dissipation. I'm not going to deal with dissipation here, but just for you to know, you just need to change the two branches of the evolution, the forward and the backward evolution, by just some quantum channel that couples both of the contours. Okay, so what's the problem here? Because all this was about staging the problem. We have mapped, or we have understood that computing the expectation value or the evolution of some observable for a many-body quantum system corresponds to contracting this two-dimensional tensor network. But it's been proven that this task is HP hard, so it requires an exponential amount of resources. In theory, we couldn't do it with polynomial resources, and this is a problem. So this is what we want to solve, or what we want to tackle with our own techniques. And usually we can start contracting this network from two sides, either from the state. If we do it from the state, we are doing Schrodinger picture, and then we keep track of all the observables for initial state. But we're going to pick today Heisenberg picture, because this is going to allow us to discuss other things. So we start from the boundary of the observable, and we start accumulating layers and layers of this trotterized evolution that we have done. And this is going to be the main discussion. And I'm going to compare it with another picture, which is a transverse picture, which, of course, since we have a square lattice to contract, we can also start from the side. And this also has a physical interpretation. It corresponds to computing what is called the influence functional in field theory. So this is a time discretized version of this object. And this is going to be the algorithm that we're going to use as a benchmark eventually. So where does the complexity come from? I said that the task of contracting the network is difficult, and I said which is the style that we're going to use, but why is it complicated? So look at the following example. If we started from the state, for example, and we start accumulating the layers, what we have is some accumulation of the virtual indices in between the local tensors. If we do not have a strategy to reduce the dimensionality of the intermediate tensors, we will have an exponential growth of the bond dimension, because we start accumulating after each step. We are multiplying the dimensions of the local tensors. And of course, after 10 steps, we multiply by 2 every time the memory that we need to represent the state, and this is not doable. So we need some strategy, and of course there is. We have strategies for truncating matrix product states. These strategies for truncation are based on the entropy of a bipartition. We pick some division between left and right. And what we use to address the singular value distribution across that bipartition. I'm going to skip the details about this, but this is a well understood and controlled technique. So we compute the Schmidt decomposition across that bipartition, and from the coefficients of the superposition, which are the Schmidt vectors, we introduce them into the expression of the entropy, and then we have some measurable quantity which is related by a logarithm with the number of singular values. And by truncating the entropy, we can truncate the dimension. We can cut out the number of singular values that we have in our distribution. So this number of singular values, or the Schmidt rank also, because it comes from computing a singular value decomposition on a matrix, is what is fixing our bond dimension after truncation. So this is going to be our measurable object of complexity of the algorithm. And of course, I spoke about the entropy. But usually we can talk about different measures depending on which is the picture that we are tackling. In the case of the state vector, we have the von Neumann entanglement entropy. And this is an entanglement measure, but this is not the case for the density matrix or for the operator. Whenever we are computing the evolution for Heisenberg picture, or in Schrodinger picture when our initial state is not pure, then the measure of complexity is called in an abuse of language operator space entanglement entropy, but this is not an entropy because it carries also information of mixture for the case of density matrix, and for the operator this is just connected to the Frobenius norm, but is not anymore informative enough of the entanglement on the system. And by extension, since we are going to also consider transverse contraction, we can also consider an entropy for the time direction for the object that is going to be the time MPS. Okay, so where's the hardness? Because we have the parameter that measures complexity. How does it grow when we fix accuracy? The problem is that even if we start from an initial state, if we quench from an initial state that is unentangled, then the evolution is going to start entangling by interaction the neighboring parties, and then eventually we'll have a matrix product state with a bond dimension that can grow with some tendency that can be polynomial or exponential. And by experience, by heuristics, all the works have detected that if we want to fix the accuracy of our simulations, namely we want to fix some quantity of error, for example, the relative deviation of the entropy when we truncate it, if we keep it to a constant value, then this imposes or asks us to keep increasing the entropy linearly. And this translates into an increase which is exponential on the bond dimension for each one of the bipartitions across the network. Since each one of these bipartitions is a square, so one of the sides is time, we say that this behavior of the entropy for keeping the accuracy constant is a volume law growth, because in this case we are two-dimensional, so volume law is anything proportional to area. And these are the 99% of the systems. Most of the systems that are non-integrable display this volume law growth of entropy. And this means that most of them are difficult to simulate, are hard to simulate, or require an exponential growth to reach the long time limit on the simulations. And this has a name. In literature, we call this the entanglement barrier. And we have an entanglement barrier for each one of the pictures, Schrödinger picture, Heisenberg picture, or even transverse picture. And this is tied to how the system demands us to increase the bond dimension when we keep accuracy constant. But of course, we aim at, or we hope that there exist polynomial techniques that can help us to still retrieve the proper dynamics without really following this exponential growth of the bond dimension. And we have cases of success in the field of tensor networks. We have, for the case of gapped one-dimensional Hamiltonians, that the ground states can be efficiently encoded as matrix product states. And there are even theorems that can assert that this is the case. So for this example, we have an analytical backup. And also for thermal matrices, we don't have much of analytical backup, but a motivation and also the heuristic experience that when we try to encode them, we do not require much bond dimension to really describe thermal matrices. And this is also a nice thing. And this is cool because we can get inspiration in these two cases in order to try to develop new techniques. In particular, since we want to represent dynamics, unitary dynamics, the exponential of the Hamiltonian, this unitary operator, is applied many times on the vector. And if we just thought on basic numerical physics, when we compute this continued application of a matrix on a vector, eventually we will expect that it's going to be projected to the leading eigenspace in case that there is a gap. The problem with unitary evolution is that it doesn't have a gap because the eigenvalues are phases. So how do we kind of connect the success cases with the unitary evolution that we want to represent? Is by introducing a gap. So at the end of the day, what we have to do is to truncate something, and by truncating is how we're going to tackle the problem and try to reduce the growth of the entanglement in whichever picture we are. Before entering in the method that I'm going to propose, let me remind you, because it's going to be a leitmotif on the talk, thermalization. I said that the generic systems that are going to display the entanglement barrier, I commented something about non-integrability, and generic non-integrable systems, which are those with a chaotic spectrum with level repulsion, they are believed to thermalize by the ETAs, entanglement thermalization hypothesis. And this means that at some point in time, if we compute the time average expectation value of local quantities, they are going to approach some stationary value. And this stationary value is going to match with the thermal density matrix in whichever ensemble we are computing the physics. For this case, the thermal matrix in canonical ensemble. And we just need to fix a temperature, the inverse temperature. And this kind of gives us some kind of intuition of why we have this complexity, this entanglement barrier. It's kind of rooted on the physics. If we start from an initial product state, we have no entanglement, and after time evolution, we want to generate an amount of entropy that matches the thermodynamic entropy. And we know from our basic lectures of thermodynamics that entropy has to eventually be extensive or proportional to the size of the system. But the entropy is connected through a logarithm with a number of singular values across the bipartition, so it's going to impose this exponential growth in order to be able to recover the thermodynamics. So this is kind of an intuition of why the physics is demanding this complexity growth. And last comment, how do we fix this temperature? Because I'm going to be talking about states equilibrating to different temperatures. We fix them with the condition that the initial energy is the same as the expectation value for the thermal density matrix. And I'm going to fix which is the Hamiltonian I'm going to use for illustration is the Ising Hamiltonian in the non-integrable point -1 -1 -0.5. And I'm going to deal with initial product states, and we can perform a whole map on the Bloch sphere of the equilibration temperature for each one of the initial energies by varying the different angles, the polar angle and the azimuth angle. Okay, so now let's shift to the proposal and to the characterization. This is going to be a bit faster. We are going to work on Heisenberg picture. And this means that we work with observables. So we have this formulation that I said at the beginning. We have my matrix product state or matrix product operator formulation in the basis of Pauli matrices. And we've seen already these Pauli strings in the Hamiltonian in the last slide, because we have terms of set giving me the interaction or the local fields sigma z or sigma x. They are Pauli strings where all the entries are identities except in the only non-local sites where I act non-trivially with my operator. What's the issue with Heisenberg picture? Whenever I start with a local observable which is expected to thermalize, I'm going to have a branching due to the commutation with Hamiltonian, and at each one of the steps, I'm going to generate amplitude on the superposition proportional to the size of the time step. And since I have some interaction that has two-side support, then I'm going to keep extending the support of Pauli matrices in my superposition. Why do I make such an emphasis on the number of Pauli matrices? We're going to see it in the following slides. But first, let me introduce some name. We're going to call Pauli weight to the number of Pauli matrices that we have on each one of the components. So, why do we talk about Pauli weight? Because one of the main proposals that achieved longer time simulations for one particular case is based on truncating this Pauli weight on the superposition. And this proposal was by Tibor Rakovszki and the team of Frank Pullman already in 2022. And they proposed how to compute expectation values of correlations that enter into the description of transport for infinite temperature. How did they do it? So basically, they proposed to introduce some soft projector which means that in our network, we introduce some MPO with some frequency, some period, delta t, that is going to erase or truncate the amount of Pauli weight. So after 4 steps of evolution, for example, I'm going to apply some decay to all the components with more Pauli weight than some threshold that I decide. And this corresponds to following or keeping track of the evolution of the strings. Those ones that have a Pauli weight that is always controlled within the threshold, they are going to be accepted in the evolution. Those that violate within a time that is shorter than the period of erasing are going to be also kept in my description, but those that escape, they're going to be erased. So it's a kind of soft threshold or soft cutoff within the Hilbert space, because what we are doing is to bound the available superposition in our evolution. Why does this make sense for their case? They wanted to compute expectation values at infinite temperature. So you just need to compute expectation values with the string of identities. And of course, string of identities has 0 sigma matrices. So by orthogonality, we will have a vanishing expectation value for anything that has Pauli weight. So truncating high Pauli weight components makes sense in this case. But how can we extend this for other initial states like thermal states or product states? Because actually infinite temperature is not like a huge achievement. We would like to describe low temperatures in quantum many-body systems. Let's first try to analyze for thermal matrices what happens. For thermal matrices, if we expand the Boltzmann weight, and this is going to be a qualitative argument, we see that we have powers of the inverse temperature. So when we compute the expectation value with the Heisenberg evolved operator, what we get is some coefficient up to the overlap, which is an order 1 coefficient with some imaginary quantity. We get powers of the inverse temperature and some measure of energy, some Frobenius norm of the local Hamiltonian that we would deal with, to the power of n. And this means that whenever this coefficient is smaller than 1, then we can expect that bigger Pauli weights are going to contribute less and less. So this gives us some idea that, okay, maybe we can even extend the method of Pauli weight truncation to finite temperatures, provided they are high enough, higher than some inverse measure of energy. But of course, if this factor is bigger than 1, then nothing ensures that this summation is going to be decaying as the Pauli weight increases. What happens for the case of product states that are the favorite states to perform toy simulations? So the scenario is much more difficult because we have all the Pauli matrices when we compute when we write everything in terms of Pauli strings. So the first thing we have to do is to simplify, try to compress all this information into a single Pauli matrix. If you take a look, I can compress all these sines and cosines into just a parallel Pauli matrix. And by definition, I can also create my orthogonal Pauli matrices by orthogonality. Once I define these Pauli matrices, I can split the Pauli weight into parallel Pauli weight and orthogonal Pauli weight. Or if you want, we can also talk about diagonal and off-diagonal Pauli weight, because this parallel Pauli matrix is the one corresponding to the axis of quantization of the initial state, is pointing towards the direction of magnetization, and the off-diagonal corresponds to this orthogonal Pauli weight spanned by the orthogonal Pauli matrices. And this splitting allows me to split also the Heisenberg superposition into 2 components, the parallel one and the orthogonal. The orthogonal that doesn't contribute has at least one orthogonal insertion in each one of the components. And as I said, by orthogonality is going to vanish. So actually we would like only to keep track of the parallel one. So maybe we could design some extension of the method of Pauli weight truncation. Instead of truncating all the Pauli weight, we can just go more concrete and truncate only the orthogonal Pauli weight, provided we have an initial product state. So we change the diagram from truncating or putting some threshold for all the Pauli matrices to putting it to just a subspace of them. For example, if the initial state is the fully polarized state, then we just have set matrices. This means that we can eliminate the Pauli matrix X and the Pauli matrix Y that are spanning the off-diagonal. So the first thing we have to do is to understand whether this proposal makes any sense. And since we don't have analytical techniques to tackle this problem, what we have to do is to characterize it numerically. The first characterization we propose is to check the contributions resolved to the Pauli weights, each Pauli subsystem. So I have my expectation value, and I introduce a sum over the projectors for each one of the available Pauli weights, and then I'm going to see the size of each one of the components for initial operators that are local and initial states that are product states. And I'm going to check two examples. The fully polarized state that for the particular point of the Hamiltonian that we picked relaxes locally to more or less low temperatures. And I'm going to compare it with another one that relaxes to higher temperatures. And this is going to have some purpose later. The first thing we see is that for the lowest Pauli weights, one insertion of Pauli matrices, two Pauli matrices, we get soon some kind of equilibration on the contribution, some constant value. And this makes sense or looks like is connected to the thermal value. This means that whenever we have some quench dynamics, we will get some oscillations, but the height of our plot is going to be fixed by the low Pauli weight components. While the high Pauli weight components, the heady strings in terms of Pauli weight, are going to give me the oscillations. And this is important because this is telling us already that if we are interested on spectral quantities, on the Fourier transform of the evolution, then actually we will only need to represent faithfully the heavy strings, or maybe just the front of the operator. On top of it, if we compare both plots, the left and the right, we see that for the one in the right, the high temperature one, we have some gap between the contributions given the direct component, the DC part, the thermal part, and the oscillations that are kind of suppressed by around an order of magnitude. And this kind of tells us, or it's kind of suggesting, that temperature is kind of rolling the difference between the two states. So there must be some impact of temperature, despite we are in Heisenberg picture. Thermalization is always talking about the density matrices, but somehow in the Heisenberg picture, we need some inheritance to explain these differences. Another check that we can do for the validity of the method is understand the backflow. With backflow, I mean how much norm in my operator is going back to the non-contributing space from the non-contributing space to the contributing space. So in order to evaluate it, we perform some evolution, we project onto the orthogonal space, then we evolve and measure expectation value I get, contributing to my initial state. And then we see already the same difference. We see that there's more backflow on the lower temperatures and a suppressed backflow for the high temperatures. So this is pointing out also that maybe high temperature states are easier to simulate if we truncate Pauli weight, even if the initial state is not thermal, but a pure state that is a product state. So without more dilation, we have tested and we have some intuition of how it's going to work. Now let's implement the method. And these are the first results. We orthogonal Pauli weight truncation with the same schemas that by Tibor Rakovszki and Frank Pullman, but we changed the dissipation and we got some really nice results. For example, for the X magnetization for initial state that is fully polarized along the Z axis, For these conditions, we have 64 spins and a time step of 0.1. We see that in comparison to the case when we have no correction, no truncation, gamma 0, then we have an oscillation that is well controlled around the thermal value. While the case that had no controlled truncation started to oscillate without a kind of unbound behavior, and we see that the error bars are big if we compare some bond dimension and half of it. We see that the convergence in bond dimension is faster for the case that truncates Pauli Weight, orthogonal Pauli Weight, but on top of it, orthogonal Pauli Weight truncation is able to catch thermal behavior and also oscillations, provided we include a low enough dissipation. So we already get some nice results, qualitative results. It's really interesting to see that even the energy is better preserved. The normal algorithms from tensor networks start detaching around time 7.5 for a bond dimension of 500 from the constant value for a case which is unitary, right? So we will expect that the energy is going to be preserved. So it soon fails, but our algorithm is able to bend back the energy and achieve this conservation to a good level. So this is a nice result. And of course, I want to emphasize that we reached time 20, which compared to the times available by normal TBD algorithms are like 7.5 or even 5. We have limited amount of bond dimensions. So this is good. We got to long time simulation and we could even go longer. I just got the simulation here for illustrative reasons. So we are happy about these results. And we see that the operator entanglement entropy is also controlled. We bend back the entanglement barrier. Eventually, despite we have an initial growth that is volume law, we are able to bend back the growth to an apparently constant behavior. So we conclude that this algorithm could be competitive, but of course we need to keep comparing it with other algorithms to be able to benchmark how good it is. In order to benchmark this algorithm and also to validate the intuitions we got about the influence of temperature, what we're going to do is to compare two transverse evolution algorithms. And these algorithms have been developed by the team in Munich, by Mari Carmen Bañuls and Miguel Frias mostly, and also introduced by Ignacio Cirac, Mari Carmen Bañuls, and Alexander Müller in 2012. And here what I'm going to do is to compare simulations for two different initial states that should relax to the same temperature. And I'm going to perform the study with our algorithm, the orthogonal Pauli Weight truncation, depicted in pink, which we call this the coherent assistant evolution. And I compare it with the transverse contraction algorithm, which is what they call the light cone algorithm. And we see a qualitative agreement. But of course, we need some study that is more systematic out of seeing that both of the plots overlap. So what we're going to do is to compare the integrated deviation between both results. And we're going to plot it in front of temperature of equilibration for the initial state. And this is one of our most remarkable results. We have seen that provided we accept that the light cone algorithm is one of the most competitive ones and is one of the most exact, our algorithm is able to approach this exact solution the higher the temperature gets. So we see this nice thick shape around the zero beta, which corresponds to infinite temperature. And when we start detaching from the infinite temperature, we start seeing that we accumulate more error. And in this case, these two plots that I showed here are the family of states that are more complicated, depicted in pink, but we have warmer states in blue, green, or yellow that have infinite temperature, and each one of the markers corresponds to an initial state. And we see that the tendency is the same for all of them. So a conclusion is that high temperatures appear to be simpler to simulate, even if the initial state is pure, because we had this argument for the thermal density matrices, but here for pure states, product states, we also see that we have some kind of dependence with temperature. There's this inheritance from the Schrödinger picture into Heisenberg picture. And we have some idea of why is it the case. I commented before that the oscillations on the observables are kind of connected to heavy Pauli strings. So since our algorithm is kind of also truncating the dimension of the Hilbert space by eliminating heavy orthogonal strings, what we're doing is also to crop these oscillations. So of course, if a state requires more oscillations to be accurately described, then it's going to be more difficult to simulate. And here, what we see qualitatively in these mini drawings that I have here is that as I increase temperature, these oscillations, the amplitude is going to close around the thermal value. And of course, the ones with less error between the light cone simulation and our simulation are the ones with infinite temperature or high temperature. But then we are also extending the regime of simulability to finite temperatures far beyond what we expected from our qualitative argument. So this is some of the discussion I wanted to do. And this brings me to the conclusions because we are already quite over time. We proposed this alternative Pauli Weight truncation, and in the process, we had to assess whether it's going to work or not. So we characterized the method. How? We characterized, first of all, that the heavy Pauli weight is going to mediate the fluctuations, and we see it by observation of our simulations. And the low Pauli weight components are going to mediate the thermalization. So the constant value to which observables are believed to reach some stationary value, even at short or long dynamics. And then this off-diagonal Pauli weight is able to achieve long-time simulation in comparison to state-of-the-art methods like the light cone. And we see that this truncation is kind of dependent on temperature. So we see this inheritance from Schrödinger picture into Heisenberg picture, which is an interesting piece of information, not only for numerical physics, but for theoretical physics. With this, I want to conclude. Thank you all. This is everything. I receive your questions from now on. Thank you.
Thank you very much, Carlos. It was very, very nice. And I open the session for questions. So any question around, please raise your hand and we will unmute you to let you. Okay, so it seems
it was a bit dense. I admit it.
It's quite technical, yeah.
Yeah.
So please, you can ask even simple questions.
Even the most simple. It can be that not even the basics could be understood. So yes, totally. If you have some interest on the basics, we can also review them. I'm okay with everything. That's why I wanted to pass more time on the setup than on the method, because the method requires like working on it more hours, and it's so interesting, but we have limited time. Yeah, tell me.
Let me just do it. I mean, so what do you exactly mean by a thermalized operator?
Okay, with thermalized operator, I mean that the expectation value across time. Okay, so let me maybe with the latest plots visually it can be seen more clearly. Okay, so this plot is the expectation value of some local operator, and I track it across time, and we see that it's oscillating around some fixed value. And this
But sorry, this you mean an expectation value, or just this is a sigma? No. So what is a component, or is just so this number is?
Yeah, this is the expectation value. It's just that I did not put the brackets, but
okay,
since I put the time dependency and I didn't put the circumflex, it's a number. It's not an operator.
Okay. No, I see. So this is a Heisenberg operator, and you call it thermalized when the expectation value reaches a constant in time, no?
Exactly. So we will
Yeah.
expect that it's going to reach a constant, but for example, in this case, we see long-term oscillations, which are also interesting to access spectral physics. But if temperature is high, like in this corner here we have finite temperature, we see that we don't have oscillations. And this one is strongly thermalizing, in contrast to this other one that is thermalizing approximately or weakly, only on average.
Yeah, I see. Uh-huh. Okay. So the Hamiltonian you've been playing around is just this transverse Ising model?
So we also use other Hamiltonians, but yes, for illustration reasons, we just use one because the results are similar. Maybe we just need like more bond dimension because some models are more complicated. For example, Heisenberg, the Heisenberg model requires much more bond dimension, but also the time scales that we have to simulate are much shorter because it thermalizes much faster.
Yeah.
But yeah. So yeah, we tried various models.
Mm-hmm. Yeah. So and with this Hamiltonian, have you found some spots where the thing is thermalizing quicker or slower? Or I mean, just playing around with the constants, I mean, the transfer field, going to some critical point or something like that.
Okay, so usually this weak and strong thermalization is rather more dependent on not only on the point of the phase space of the Hamiltonian, but also on the initial state. Usually, it's the initial state the one that is kind of indicating how many fluctuations we are going to have.
That's it.
Once you fix the point of the Hamiltonian. It's true that some points of the Hamiltonian, especially when you're close to integrability, then you approach conformal field theory points, then we have long-term oscillations.
Yeah.
But yes, it's strongly dependent on the initial state also.
Yeah. And a final question. So, um, you have this dissipation. So what are the knobs you have? You have this dissipator now that caps off the heavy strings. Yeah. Does it have a parameter or is it?
Yes. Yes. Yeah. Sorry. Maybe I skipped it. So this dissipation, it's similar to the one that this collaboration wrote. This generic Pauli Weight truncation. So this object is a matrix product operator that basically reads the superposition and counts how many Pauli matrices I have. In our case, counts the orthogonal ones, not all the Pauli matrices. And when you pass the threshold, and this threshold is the first knob, the first hyperparameter of the algorithm, this omega star, then I apply some decay e to the power of minus gamma, and gamma is the strength of the erasure.
Mm-hmm.
And
So
then
depending on,
the other hyperparameter is how frequently I do this.
yeah. So then how do you choose the final temperature? This is selected by the initial energy or?
The initial energy, yes.
And should there be any correlation between this parameter and the temperature to to keep some, I don't know, efficiency of the method or, I mean,
Yeah.
the way you.
So the method actually we will have to aim at an extrapolation to zero dissipation. So we want to see some convergence on these parameters. The pictures I have shown is just a hand-picked point just to show in an illustrative way that the method is reaching good results. But of course we will have to do some extrapolation.
Yeah. Mm-hmm.
But indeed, usually in the original work, they fix all the knobs excepting one, which is the strength. And then they repeat the same simulation for strength 0.1 or 10 to the power minus 2, minus 3. And then they try to do some extrapolation for the quantities they want to estimate.
Well, I mean, for example, for very high temperature, is this dissipation has to be stronger or
So for
to
high
reach?
temperature, what we observe is that it's not that it has to be stronger, but you are free to use this to set it much stronger. The stronger it is, the more the operator entanglement decreases, and therefore the lower the bond dimension is. So for higher temperatures, then it's easier to simulate because you are free to just erase more and more.
I see. Very interesting. Very interesting. So, last chance for a question. Yeah, there's some probably a very basic question, but how beta can be negative? Isn't it 1 over k boson times t? 1 over t.
Yeah.
1 over the temperature.
Okay, so yeah, this is one of the nicest questions we always had since the degree of physics, the lecture courses on statistical mechanics. So statistical physics doesn't forbid you to have negative temperatures. What it forbids you is to have zero temperature. But around the zero temperature, you can have plus infinity, minus infinity, and plus zero, minus zero. So you have like just these 2 points that are excluded, but your systems can have negative temperatures. Physically, what does that mean? A negative temperature system is a system that is prepared in an extremely high energy state. For example, these negative temperatures have been observed in NMR experiments. I think the first moment in which they were discovered historically is for the nuclear magnetic resonance, and you can prepare the system in a state that is highly excited. So, for example, imagine you have a system of spins, and you have an external magnetic field. You put them against the magnetic field, and then this state is highly excited, and it's kind of metastable. And then it thermalizes to negative temperature. So you can have negative temperature systems, and they are long-lived in other setups, not only on NMR, but also in bosons, in lattices, in these analog quantum simulators. And they have interesting properties because, for example, they are hotter than positive temperatures because they can provide much more heat by transfer. But yeah, this is like the few things I know from the courses of statistical physics. But yeah, like it's completely allowed. Yeah.
Julia is answering, so she probably ever is it? So perfect. Thanks. So she's happy with the answer.
Okay.
Thanks, Julia, for contributing. So thanks everybody for joining us today, and we reconvene in 2 weeks with this series of seminars up to the end of the project, Quantum Spain. So stay tuned, and thanks to Carlos for this contribution.